Okay, so this video looks at the first part of the energetics topic. So the AQA spec breaks it down into 4 parts: enthalpy change, calorimetry, Hess cycles, and bond enthalpies. And so this video looks at the first of those, enthalpy change. So we've got the spec code 3.1.4.1. You should always refer back to the specification repeatedly through the course to check exactly what is it that the AQA spec is telling you that you need to know. And so we begin with this enigmatic sounding word, enthalpy. Now, enthalpy is represented by the symbol H, and it refers to the heat content of a substance. Now, I don't think that really helps you to appreciate what's happening. And in fact, you can't measure it directly, but what you can measure is its change, and that's what we're really interested in. And so what we're really looking at here is the change in enthalpy, or rather the energy transfer. And energy transfer is something you are already familiar with from earlier in your school life. So when we're talking about enthalpy change, we're talking about the energy transfer during a reaction. H, as we said, was the symbol for enthalpy, and then we have the Greek letter delta, and that's a capital letter, and that basically means in science, represents a sizable change or a sizable difference. So we are already familiar with a lowercase version of delta that we came across when we were looking at bonding and we were looking at partial charges. So the letter delta represents a change, a capital delta, the triangle, represents a sizable change, and the lowercase delta, the one that looks more like a conventional D, represents a very small change or very small difference. So we're using delta H to signify a change in enthalpy. Now the other thing to mention is that we are usually using the units kilojoules per mole. Now it is possible to work out the energy transfer in joules per mole, but like I say, the final units for enthalpy change are typically kilojoules per mole, and you quite often have to convert joules into kilojoules in a calculation. But the crucial thing is that it's an energy transfer per mole. Okay, so we're absolutely looking at per mole here. Now, when you've done energy transfers before, you've spoken about reactions being exothermic or endothermic. So here you were describing whether the enthalpy change was a transfer of energy to or from the surroundings. So if you described it as being exothermic, then energy was transferred to the surroundings, and endothermic was from the surroundings. And you would have considered reaction profiles like the one shown here. Now, to help us appreciate these reaction profiles a little bit better, I think it helps to think of the y-axis as a measure of the chemical store of energy. So if the reactants have a greater chemical store than the products, then the chemical store decreases during the reaction, and as energy cannot be created or destroyed, it can only be transferred from one store to another, it must be transferred to the surroundings. Alternatively, if the products have a greater chemical store than the reactants, then the chemical store increases during the reaction, and the difference must have been taken in from the surroundings. Now, it's helpful to think of the y-axis as a measure of chemical store, but actually in A-level chemistry, what that y-axis represents is enthalpy, is that heat content of the substance. What that means is if we look at the change in enthalpy in an exothermic reaction from reactants to products, we can see that the change is negative. So that change is a negative change, so it's decreased. And if we look at the endothermic reaction, we can see the change is positive. And that's going to be helpful for when we're thinking about the appropriate sign in front of our values. Will depend on whether the reaction is exothermic or endothermic, and our clues as to whether it is exothermic or endothermic will be things that we are familiar with already: an increase in temperature of the surroundings, a decrease in temperature of the surroundings. So one of the key differences regarding energy transfer between A-level chemistry and GCSE chemistry is that predominantly at GCSE we talked about energy transfer qualitatively. We said it was exothermic or endothermic. We said the surroundings got hotter or colder, but we didn't really have any values, any sort of sense or measure of actually to what extent or how much energy was transferred. The only time we did that at GCSE was when it was bond energies. And bond energies are going to feature in this topic as well. They're going to be the 4th part of the specification for energetics. But mostly we considered energy change qualitatively. Now at A-level, we do it much more, it's much more of a quantitative topic. And so it's going to involve a lot of calculations. Now, for us to be able to do those, to be able to use the data that's supplied, one of the things that we need to get our head around are definitions of some particular enthalpy changes. Now, just before we look at the actual definitions of these enthalpy changes, if we're going to make a fair comparison between energy changes, then they all need to take place under the same conditions, and we call those conditions standard conditions. And we represent the fact that they are standard using that Greek letter theta. So theta there means under standard conditions. So standard conditions are a temperature of 298 Kelvin or 25 degrees Celsius. So that is roughly room temperature. A pressure of 1 atmosphere, which is approximately 100 kilopascals. Again, that's roughly the pressure you would expect at sea level. Substances have to be in their standard state at these temperatures and pressures. So, for example, oxygen is a gas and sodium is a solid. And then if there are any solutions involved, they will all have to have a concentration of 1 mole per decimeter cubed. So ΔH was the symbol or representation for enthalpy change, and now if we use a superscript theta, what that's saying is it's the change in enthalpy under standard conditions. So it represents ΔH standard. So the first definition is for the enthalpy change of formation. So you can see we've got our ΔH representing enthalpy change. We've got a subscript F to represent formation, and we're saying with our superscript theta that it's all taking place under standard conditions. So what does it mean? It means the enthalpy change when 1 mole of a substance is formed, hence the formation, but crucial is this 1 mole bit here, from its elements in their standard states. So I think it will help us appreciate that definition if we actually see an example of that. So here we're asked to represent the enthalpy of formation, or the equation for the enthalpy of formation of sodium oxide. And so this equation has to satisfy that definition that we have above, that 1 mole of a substance is formed from its elements in their standard states. So the way to approach this, if you've got enthalpy of formation, is you know what's being formed. So draw the reaction arrow and draw the substance, or write the substance being formed. And the thing is, because we're making 1 mole of that substance, what that means is from now on, when we complete the equation, this cannot change, and we cannot put a number in front of it, because that represents the molar ratio of 1 mole. We should do the state symbols as we go along. So sometimes you're told them, sometimes you are expected to know them, and sometimes you're expected to work them out. So if you think about this compound, our useful rule of thumb is to look at the types of elements that make it up, and we have a metal and a non-metal. So this is going to be an ionic compound, and one of the things that we know about ionic compounds is that they have high melting points, and under standard conditions, which is basically room temperature, room pressure, so the environment that you're familiar with, sodium oxide or ionic compounds would be solid. So the definition says from its elements in their standard states. So we have to think about what elements make up sodium oxide. So clearly they're sodium and clearly they're oxygen. And so we have to represent those elements as they would be represented under standard conditions. So Na, sodium, and we know it's a metal, and we know it's a solid at room temperature, and then plus oxygen, and we know that oxygen is a gas, and we also know it's O2 molecules. So you have to remember these particular things. You have to remember which elements are diatomic. You have to remember which elements are solids and gases. And now we need to balance it. We need to make sure that we have the correct molar ratios. Now we cannot change what's on the right-hand side. So we've got to have the equivalent of 2 moles of sodium atoms on the left, and we've got to have 1 mole of oxygen atoms on the left. So we're going to put a 2 in front of the Na. And at the moment on the left, we've got 2 moles of oxygen atoms, and we only want 1. So we're going to have to put a half. So that half doesn't mean half an oxygen molecule. What it means is half a mole of oxygen molecules, which would be a mole of oxygen atoms. Now let's look at the second one, which is the enthalpy of formation of ethanol. So the first thing we know is that we are making ethanol. So we're going to draw our reaction arrow, and we're going to put 1 mole of methanol on to the right of that. So we're making 1 mole. That's our 1 mole of a substance formed. Ethanol is a substance we should be familiar with regarding its state. It's a liquid, so that we put a state symbol. And then we think of what elements make up ethanol, and we've got carbon, we've got hydrogen, and we've got oxygen. So the next thing we should do is just write those elements on the left-hand side. Got to remember that hydrogen is diatomic, and we've got to remember that oxygen is diatomic. And carbon is a solid, so that was a giant covalent structure. The only forms of carbon that you're familiar with are graphite and diamond and the fullerenes. But anyway, so that's going to be carbon as a solid. Our hydrogen is going to be a gas, because hydrogen is a gas, and oxygen obviously is a gas too. So next we have to make sure that they're balanced on the left-hand side. So let's look at how many atoms of carbon there are on the right. So we've got 1, 2. At the moment we've only got 1 on the left, so we're going to have to put 2 in front of that. How many of hydrogen? We've got 1, 2, 3, 4, 5, 6. At the moment we've only got 2. So on the left, so we're going to have to put a 3 in front of that. And then finally, we've got 1 oxygen on the right, and we've currently got 2 on the left. So we're going to put half there. So just to recap, we are forming 1 mole of a substance. So when we get the ΔhF, it will give the substance that we're forming in brackets. So that has to be what goes on the right. It will be the only thing that goes on the right because it's a single product. The arrow will go to it, and there cannot be a coefficient in front of the formula because we are making 1 mole of a substance. So everything has to stem from this very first action that we do. Then the left-hand side has to be the elements that make up that substance, and those elements have to be in their standard states. So you've got to appreciate what the formula of that element would be, and you have to appreciate what state it would be in under standard conditions or at room temperature and pressure. And then you've just finally, the last thing you do is you balance so that you have the same number of each type of element on both sides. So here are 4 more examples. So what I suggest you do is you pause the video and have a go at writing the first one, and then I'll show you the answer and just talk you through, and then we're going to pause the video again and you're going to have a go at the remaining 3. So pause the video now. Okay, so the answer to the first one is, so we were doing the enthalpy of formation of magnesium chloride. So the first thing we did is, or we should do, is draw the reaction arrow and write the formula of magnesium chloride. And we are never going to put a number in front of a coefficient in front of the formula because we are making 1 mole of the substance. Think about what type of substance magnesium chloride is. It's an ionic compound, so at room temperature and pressure it's going to be a solid because they have high melting points. What elements make up magnesium chloride? Well, magnesium, and that is a metal, so we put an S because we know it will be a solid at room temperature. And chlorine, we have to remember that chlorine is a diatomic element, and so it's going to be also a gas because we know chlorine is a gas at room temperature. And then we would check that our equation is balanced, and it is balanced, and then that's it finished. Why don't you pause the video now and have a go at 2, 3 and 4, and then I'll give you the answers. So pause the video now. And there are the answers. So what could you have been caught out by? So you may not have been familiar with the fact that ammonia is a gas, but by the end of the course, I think that should be something that you would know. Hopefully you didn't forget that nitrogen is a diatomic molecule, and then obviously both of those elements are gases. What else about the third one? So I think what you could have been caught out by is the state of bromine. It's one of only 2 elements that's liquid at room temperature. Otherwise, I hope it was okay, but of course if there's anything you're not unsure about, please just let me know. The second definition that we need to know is the enthalpy change of combustion. So you can see that like enthalpy of formation, it's represented by ΔH to represent enthalpy. Naturally, it's under standard conditions, hence the superscript theta. And then to make it clear it's about combustion, we have that subscript C. So when we're considering what the definition for that enthalpy change is, it's when 1 mole of a substance is, so there's that 1 mole again, is completely burnt in oxygen. So we are always assuming complete combustion. So you may have done a GCSE, particularly with the organic part of the topic, or with hydrocarbons, the idea of complete and incomplete combustion, and that is something that features in A level. But as far as the definition is concerned, you always have enough oxygen for the substance to be completely burnt. So the difference here is that whereas with formation we knew what was to the right of our arrow, with combustion we know what's to the left of our arrow. So we know we are combusting sodium, and we know that we are combusting 1 mole of it, so we are never going to put a coefficient in front of the formula. Sodium is a solid, so we may as well get the state symbol down so that we don't forget. And we are reacting it with oxygen because that's the whole point. It's completely burnt in oxygen. And then we have to think of our product. And if you remember, even from lower down in school, a metal plus oxygen equals a metal oxide. So this is going to be sodium oxide, and it is a substance that you need to be able to work out the formula to. So I'm just going to write the formula. It's Na2O. Because sodium is a group 1 metal, and so it's going to have a 1 plus charge, and oxygen is group 6 non-metal, so it's going to have a -2 charge. So you need 2 sodiums for every 1 oxide ion. So it's a 2-to-1 ratio. Remember, these are empirical formulae. They represent the ratio of the ions. And it's an ionic compound, so it's going to be solid. And now it's a question of balancing. So we cannot change the substance that we're burning, so we cannot put a number. So what we've got to decide first of all is we would look first of all at the product from the element that we were, or from the substance that we were combusting. We have 1 sodium on the left, we currently have 2 on the right. So what that means is we have to put we have to put a half in front of the sodium oxide. So that will now give us 1 sodium atom on the right hand side. Or 1 sodium is not an atom, but 1 sodium on the right hand side. Now, what does that mean about oxygen? That means on the right we've got half an O, or half a mole of oxygen atoms, whereas on the left at the moment we've got 2 moles of oxygen atoms. So to make that half a mole of oxygen atoms, we have to write a quarter. So one of the things that you may have noticed already from the formation equations, but also you'll particularly notice it now, is that it's fairly common to have sort of fraction coefficients, and especially fractions that are less than 1. That is perfectly fine for these enthalpy changes for formation and combustion, because what really matters is that you are following the definition, right? You are following the definition and just meeting that definition. So if we look now at ethanol, so we are combusting ethanol, so that is going to be on the left hand side, and we know that ethanol is a liquid, and we know we are combusting it in oxygen. So at the moment we're just writing the formulae, and if you combust an alcohol, you always get carbon dioxide, and that's a gas, and you always get water, and at room temperature and pressure that is a liquid. So now it's a question of balancing. So we cannot change the number of moles of ethanol. It has to have no coefficient, so it has to be 1. If we look at how many carbons we've got 1, 2 on the left. We've currently only got 1 on the right, so we're going to need to make that 2. And then we look at how many hydrogens there are. So 1, 2, 3, 4, 5, 6. So we've got 2 on the right, so we need to put 3. And now we turn to the oxygens. Now, just something to point out, there's a couple of things actually to point out, but one of the things is when you have a combustion reaction like this, or in any reaction, if you have an element appear in more than one substance on one side of the equation, so if we look at the right-hand side, we can see oxygen appears in 2 different substances, then when it comes to balancing, you should leave that till last. You should leave any element that appears in more than one substance on one side of the equation, you should leave that to last when it comes to balancing. The other thing to mention, and something that is easy to miss, is that when we come to balance the oxygens now, we must not forget about the oxygen in ethanol, right? So we have 1 oxygen in ethanol there. So how many oxygens have we got on the right? We've got 2 times 2, so that's 4, plus 3 times 1, so that's 3. So 4 plus 3 is 7, so we've got 7 on the right. We've got 1 from ethanol, and that cannot change. So that means we've got to get 6 from our O2, so we need to put a 3 in front of it. And that now is our balanced equation for the enthalpy of combustion of ethanol. So like before, what I'd like you to do is, I want you to go have a go at these, but maybe just do the first one to begin with. So do propene that we've got there. So if you could do the enthalpy, the equation that represents the enthalpy change of combustion for propene, pause the video and then I'll show you the answer, and then I'll just talk you through it, and then we'll have a go at 2, 3 and 4. So if you'd like to pause the video. So the equation that represents the enthalpy change of combustion for propene is, so we obviously had to keep our C3H6 fixed as 1 mole. If you combust a hydrocarbon, you need to know that you're forming carbon dioxide and water. Obviously, the whole point of combustion is it's completely burnt in oxygen. So then it was a case then of balancing the equation. You could put in front of the O2, you could write 3.5. So 3.5 would be acceptable, just as 7/2 is acceptable. The only thing I'd say is I personally use fractions because I think it makes it much easier and quicker to count how many atoms, because basically the denominator 2 and the 2 after the O basically cancel each other out. So straight away I know that I've got 7 atoms or 7 oxygens. So I just feel it's much quicker than having to convert 3.5, which, okay, maybe isn't that tricky, but it's just an extra step, isn't it? Anyway, if you want to now have a go at 2, 3 and 4, and then pause the video, and then I'll show you the answers. So pause the video. Okay, so the answers to 2, 3 and 4 are. So check how your answers compare with that. The only thing really, I guess, to say is, look, we've got a really interesting fraction in the third one in front of our oxygen. We've got 3/4 O2. That's because we needed 1.5 moles of oxygen atoms. So I hope that's been okay. That's the first section, the first 4 sections on energetics. So this covers enthalpy change. If you've got any queries, let me know, and I'll do my best to help.